On the 29th of May 1919, on the island of Principe and in Sobral, Brazil, astronomers aimed their cameras at an eclipsed sun and tried to measure something that sounded almost impossible: whether gravity could bend starlight. If the stars near the sun appeared slightly shifted, Einstein's new picture would be right, and Newton's calm, clockwork cosmos would be missing a secret. When the plates were developed, the result traveled faster than the science itself. Gravity was no longer just a pull. It was a sculptor of space and time. That single eclipse opened a door we still haven't closed. Because the deeper physics goes, the stranger gravity becomes. It holds galaxies together, yet seems absurdly weak beside the other forces. It shapes black holes, yet drives our best theory into breakdown at singularities. It sends ripples across the universe, confirmed on the 14th of September 2015, when LIGO recorded gravitational waves for the first time, yet may refuse to reveal its smallest unit, the graviton, as if nature built a lock into the laws. For more than 3 centuries, gravity has invited bold hypotheses. Hidden dimensions where it can leak away, modified laws that change at tiny accelerations, and the radical possibility that gravity is not fundamental at all, only an emergent effect of information and entropy. Stay with this journey, and you won't just collect ideas. You'll watch the moments that made scientists doubt their own foundations and decide what gravity is really trying to tell us. Before it bends starlight or ripples across the sky as a wave, it arrives in the smallest moments, as the quiet insistence of your own weight meeting the floor. Long before anyone gave it equations or a name, gravity was already tutoring us in silence each time a child jumped, a cup slipped, or an aging body rose carefully from a chair and felt the world hold it down. Picture an ordinary morning. Someone reaches for a glass on a shelf that is just a little too high. Fingers miss. The glass tilts, leaves the edge, and for a brief, suspended instant it seems to hang in the air. Then the familiar rush downward. The sound on the kitchen tiles. The small disaster. No one in that room thinks, in that moment, about the structure of space-time. They simply feel the inevitability. Things fall. They always have. A child learns this long before they learn words like force or mass. A toddler pulls themselves up on a table, lets go, and drops straight back onto the floor. The lesson is not written on a blackboard. It is written into the body. Knees, palms, the soft thud of contact. Again and again, the world reminds us there is a direction things prefer to go. Downward. Toward something. Toward the planet that is quietly pulling on every muscle, bone, and breath. For an older body, the lesson comes with a different tone. Rising from a chair is no longer effortless. There is a pause. A small calculation. Hands press on armrests. Legs push back against the floor. The same invisible pull that once made jumping feel light, now makes standing feel heavy. Gravity ages with us, not because it changes, but because we do. Yet it remains the one companion that has never left, from the first fall to the last step. It is strange, then, that for so much of human history this constant presence went unnamed in any precise way. People spoke of weight, of heaviness, of things falling by their nature. But the idea that every stone, every planet, every star might be participating in a single shared rule was not obvious. The sky and the ground felt like different kingdoms. What happened up there belonged to gods and spheres. What happened down here belonged to mud and bodies and rain. The legend that Isaac Newton watched an apple fall in a garden is probably simplified, polished by time and retelling, but there is a reason the story sticks. Not because a fruit dropped from a branch for the first time in history, but because someone who lived with the same everyday falling that we do realized he could ask a forbidden question. What if the force that pulls an apple to the ground is the same as the force that keeps the moon from drifting away? In the 17th century, that was not a small thought. The moon had always been part of the heavens, the realm of regular cycles and perfect circles. Cannonballs and apples belonged to the messy world below. To suspect that a single invisible rule might bind them together was to quietly erase a border in the human mind. One universe instead of two. One kind of matter instead of celestial and earthly kinds. One shared gravity. Newton wrote a law for this. Every mass attracts every other mass. The strength of that attraction depends on how heavy the objects are and how far apart they sit. There was nothing ornate in this statement. It was almost shockingly simple. Yet, with it, the motions of the planets could be described with a precision that felt uncanny. The paths of comets, the fall of stones, the ocean's tides, and the orbits of moons all fell into alignment under one mathematical lamp. For many generations, this gave the universe a particular mood, predictable, clockwork. If you knew where things were and how fast they were moving, you could, at least in principle, calculate where they would be later. Gravity, in this picture, was like an invisible network of threads woven between every object, tugging them this way and that. The cosmos became a vast machine whose cogs never slipped, whose gears could be modeled on paper. And yet, even in his own time, Newton was uneasy about one feature of his creation. He did not like the idea that one object could reach across empty space and pull on another with no intermediary. Instant action at a distance felt suspicious, almost magical. He could write the rule. He could show that it worked. But when pushed about the mechanism, he reportedly said he framed no hypotheses. The law was astonishingly effective. The reason behind it remained blank. This is one of gravity's oldest tricks. It allows us to predict without quite understanding. We can calculate where the moon will be in the sky on a specific night many years from now. We can send a spacecraft on a path that slings around planets, borrowing their motion with precision measured in kilometers, or rather, in carefully spoken distances far beyond everyday experience. We can do all of that while still not knowing why there is a gravitational field at all, only how it behaves. By the late 19th century, hairline cracks began to appear in this clean, mechanical picture. Astronomers charting the orbit of Mercury noticed that its closest point to the Sun drifted slightly more than Newton's law predicted. The difference was tiny, a small residual advance of the perihelion, but it was stubborn. It would not go away with better measurements. It was as if the inner planet were whispering that the gravitational story was correct enough to be useful, but not quite complete. At the same time, experiments with electricity, magnetism, and light were telling a different kind of unsettling story. The speed of light seemed to be the same for all observers, no matter how they moved. Time and space, which had been treated as a neutral stage in Newton's play, began to look less innocent. They bent under the weight of this new evidence. Something about the very fabric on which gravity operated was under question. There is a psychological pattern here that is as important as the physics. An old, successful theory is comforting. It has guided ships, predicted eclipses, helped build bridges and machines. It is part of culture, education, national pride. To let go of it, even partially, feels like stepping off a familiar path into a fog. Small discrepancies can be ignored for a while. They feel like noise, but as they accumulate, as Mercury insists on drifting, and light insists on its own stubborn speed, they begin to sound less like noise and more like a quiet chorus saying, "You have missed something." Gravity, perhaps more than any other force, lives at this intersection of comfort and unease. It anchors us to the ground. It keeps our coffee in its cup. It holds the atmosphere around our planet and binds stars into galaxies. Without it, there would be no planets to stand on at all. At the same time, the more attention we pay to its details, the more it seems to hint at deeper layers of reality that we have not yet named. You can see this tension even in the way culture has used the language of weight and falling. In religious texts, people speak of the burden of sin, the weight of guilt, the fall from grace. In literature, characters fall in love, fall from power, fall into despair. In philosophy, thinkers have written about the heaviness of existence, the pull of obligation, the gravity of a decision. None of this is about physics. And yet, the metaphors are not random. Something in us associates being pulled, being held, being unable to escape, with the way life feels. It is tempting to say that gravity is therefore a poetic symbol for fate or emotion, but we can turn that around. Perhaps the reason we reach for gravity as a metaphor is that we live with it so intimately that it becomes the natural language for anything that feels inevitable. When you cannot see the thing that is shaping your path, but you feel its effects constantly, you borrow the language of gravity. You say you are weighed down, or drawn in, or falling. You say you are under the influence of something you cannot quite define. There is a quiet irony here. The force that seems most familiar in daily life is also, at its core, one of the forces we understand least. We know how to calculate its effects with extraordinary precision in many situations. We know how it guides planets, bends light, and shapes the large scale of the cosmos. But when we ask what it is, not just what it does, our answers begin to break apart into different schools, different metaphors, different incomplete pictures. That is the thread this whole journey will follow. Each chapter is a different way of looking at gravity. Sometimes the views will conflict. Sometimes they will overlap. Sometimes they will feel like descriptions of completely different worlds, until you notice that they are all trying, from different angles, to touch the same silent presence that keeps your feet on the ground and the moon in the sky. The question underneath them all is simple to say and hard to answer. What is the thing that is really pulling us down? Up to now, we have spoken as if gravity were a literal pull, an invisible hand reaching out through space to tug on objects. That picture works for building bridges and plotting orbits. It belongs to Newton's age, and it still earns its keep in countless calculations. But if the old stage of space and time is shaky, if light and mercury and other experiments are hinting that the arena itself is flexible, then perhaps gravity is not a pull at all. Perhaps it is the way the arena curves. This shift from force to geometry, from pulling to bending, is not just a technical adjustment. It is a change in how we imagine reality. Instead of asking how objects tug on each other across emptiness, we start asking how matter tells space and time how to shape themselves, and how that shaped space-time tells matter how to move. The apple falling from the branch, the child jumping off a step, the planet orbiting a star, all become stories not of strings pulling, but of paths traced on a surface we cannot see but can infer. In the 19th century, no one looking at a dropped stone could have guessed that describing its fall with ultimate precision would require rewriting the concept of time itself. And yet, that is where the small whispers led. The drifting of mercury, the strange behavior of light, the mathematical discomfort with instant action at a distance. All of them were like subtle ripples on a surface, clues that the familiar stranger we call gravity had more to say. Imagine someone standing on a bridge above a river. They pick up a small stone, feel its weight in their hand, and then let it go. The stone falls, hits the water, and disappears. To the person watching, this is the most ordinary scene in the world. But hidden inside that simple arc is a story that will lead, step by step, to curved space-time, to black holes, to gravitational waves, and to questions about quantum information and the structure of reality itself. To follow that story, we have to walk away from the idea of gravity as a mere pull and step into Einstein's world, where the fall of a stone is the straightest possible path in a universe that is not as straight as it looks. For a falling stone to be the straightest possible path, space itself has to be allowed to bend, somewhere, quietly. The idea had to arise that what feels like a pull might really be the shape of the stage under our feet. In the early years of the 20th century, that idea began to take over the life of a man who, for a while, was not a professor or a celebrity but a civil servant sorting other people's inventions. Albert Einstein worked in a patent office in Bern, reading proposals for new machines and devices, checking their logic, learning to distrust complicated mechanisms that did not really do anything new. Around him, telegraph lines, electric lights, and early radios were remapping human experience. Inside his mind, a different remapping was taking place. He had already shaken the world once. Special relativity had told physicists that there is no single, universal clock ticking the same for everyone. Time is woven together with space into something that depends on how you move. The speed of light is the same for every observer, no matter their motion. And trying to keep Newton's absolute time intact only leads to contradictions. This was unsettling enough, but there was a problem that would not go away. Gravity, in Newton's picture, acted instantaneously. The sun pulls on Earth. Earth pulls on the moon. If the sun were somehow to vanish, Newton's equations implied that Earth would know right away. No delay, no travel time, just an immediate change in the cosmic balance. Yet special relativity insists that no influence, no signal, no cause can travel faster than light. Gravity, apparently, had not read the new rules. Einstein could have treated this as a technical glitch. Instead, he took it personally, almost literally. He later described a thought that came to him as the happiest idea of his life. Imagine, he said, someone falling off a roof. For the few seconds while they are in free fall, they feel weightless. Their body, their stomach, their limbs all float relative to them. If they hold a key or a pencil, it hovers in front of them instead of dropping. Inside that tiny moving frame, gravity seems to vanish. Now imagine a different scene. A person is standing in a small room in deep space, far from any stars or planets. There is no gravity there, but the room is being pulled upward by a cable. Accelerating, the person feels their feet pressed against the floor. If they let go of a pencil, it falls to the floor. To them, it is indistinguishable from standing in a gravitational field. No experiment inside that sealed box, as long as they cannot see outside, can tell whether they are in a gravitational field or in an accelerated rocket. The equivalence principle, the core of Einstein's new approach, lives in this comparison. Free fall cancels the feeling of weight. Acceleration creates a feeling of weight. Gravity and acceleration are, in a deep sense, locally indistinguishable. That harmless observation is a doorway. If gravity and acceleration are equivalent, then perhaps what we call a gravitational field is not a mysterious pull, but the way space-time itself behaves when frames accelerate and paths curve. For years, Einstein wrestled with this idea. He learned advanced mathematics he had previously avoided. He corresponded with friends who were more fluent in geometry, chasing an expression that would translate this physical intuition into equations. Unlike Newton, who found his laws early in life, Einstein carried the burden of this new gravity through a difficult decade, across personal troubles and the beginnings of the First World War. On November 25, 1915, he finally stood before the Prussian Academy of Sciences and presented the field equations of general relativity. In compressed symbolic language, they say that the curvature of space-time is directly related to the distribution of mass and energy. Matter tells space-time how to curve. Curved space-time tells matter how to move. A falling stone is not being yanked downward by an invisible thread. It is following the straightest possible line through a geometry that is not flat. This idea is abstract when stated that way. It becomes more tangible with a picture that is now almost cliché, but still useful if handled gently. Imagine a stretched rubber sheet. Place a heavy bowling ball in the middle. The sheet sags. Now, roll a smaller marble near the edge. Its path bends inward, not because the bowling ball reaches out with a force, but because the sheet is no longer flat. The marble is simply following what, on that bent surface, counts as the straightest path. The real space-time of relativity is not literally a rubber sheet, and the analogy breaks down if you push it too far. But as a first feeling, it helps. Gravity becomes geometry. The moon is not tethered to Earth by an invisible string. It is moving along the natural path in the curved space-time created by Earth. The same is true for the Earth around the Sun, for comets and asteroids, even for light itself as it passes near massive bodies. If this was only a beautiful reinterpretation, it might have remained a philosophical curiosity. But general relativity made concrete, risky predictions. One of them concerned the orbit of Mercury. Newtonian gravity had always been slightly off in explaining the slow rotation of Mercury's orbital ellipse around the Sunday. When Einstein applied his equations, the discrepancy evaporated. The extra precession fell out naturally from the curved spacetime near the Sunday. It was as if Mercury had been waiting, for decades, to confirm that gravity really is geometry. Another prediction was bolder and more shocking to the everyday imagination. Light should bend when it passes near a massive body, not because light has weight, but because it follows the straightest path in a curved geometry. Near the Sun, the paths of starlight passing just by its limb should tilt slightly inward. To an observer on Earth, those stars would appear shifted away from their true positions. The effect is tiny, but tiny is not the same as unmeasurable. On May 29, 1919, the Moon passed in front of the Sun in a total eclipse. For a brief time, the sky around the darkened Sun filled with stars bright enough to photograph. On the island of Principe, off the coast of Africa, and in Sobral, Brazil, teams led by Arthur Eddington and others set up telescopes and cameras. They took long exposure photographs of the star field near the Sun during the eclipse and later compared them to reference plates taken when the Sun was elsewhere. The story of those measurements is more complicated and more human than the myth sometimes told. The data were messy. Some plates were blurred by weather and equipment issues. Choices had to be made about which images to trust. But when the analysis was complete, the deflection of starlight appeared to match Einstein's prediction better than Newton's. News traveled quickly. Headlines around the world declared that starlight had been bent, that a new theory of gravity had been confirmed, that space and time themselves were no longer rigid. For the public, it was a rare moment when abstract mathematics and the drama of human effort met in a single image. Tiny dots of light slightly displaced, carrying the weight of a deep conceptual shift. For physics, it was a validation that general relativity was not just philosophizing, but a tool for making contact with reality. The implications were far-reaching. If gravity is geometry, then time does not flow at the same rate everywhere. Near a massive object, time runs more slowly. This is not metaphor. It is a measurable effect called gravitational time dilation. Clocks that sit on the surface of Earth tick more slowly than clocks on distant satellites. If you place a precise atomic clock on the ground floor of a building and another at the top, the one higher up will tick slightly faster because it sits in a weaker gravitational field. In our era, this is no longer a thought experiment. The Global Positioning System uses satellites that carry clocks and talk to receivers on the ground. The signals rely on precise timing to determine positions. If engineers ignored general relativity and treated time as Newton did, the timing errors would accumulate, and the positions on your phone's map would drift by many meters each day. Quietly, with no romance, your navigation app is correcting for curved space-time. Again, gravity shows its dual character. It is the same thing pinning your body to your seat and keeping your coffee in the cup, and the same thing making satellite clocks tick differently and bending starlight. The everyday and the cosmic are not separate stories. They are two ends of one geometry. When filmmakers and artists borrow these ideas, they give them back to us in a form that is easier to picture. In the film Interstellar, there is a sequence where astronauts land on a world that orbits close to a black hole. For every hour spent on that world, many years pass for someone far away. The details in the film are not a perfect textbook, but the core image is faithful to general relativity. Strong gravity distorts time. It stretches the gap between events in a way that cannot be undone. To think of gravity in this way is to let go of the instinct that it is a force pushing or pulling. Instead, we are invited to imagine ourselves as moving along the straightest paths available in a landscape made of space-time, a landscape whose hills and valleys are carved by mass and energy. Standing still on Earth's surface, you are not truly at rest. The ground is pushing up on you, preventing you from following your natural free-fall path through curved space-time. The weight you feel in your legs is the echo of that deflection. This reinterpretation also changes the kinds of questions we ask. In Newton's universe, we might ask, what is the exact form of the force law between two objects, and can we modify it? In Einstein's universe, we ask, Why does mass and energy cause curvature at all? Why are the equations relating curvature and energy of the specific form Einstein wrote down? Could they have been different? Are they emergent from deeper statistical rules? For many physicists, general relativity has a special status because of its elegance. The equations are compact, symmetric, and, in some sense, inevitable once you accept the equivalence principle and a few reasonable conditions. The theory has passed every test thrown at it on scales from the lab to the solar system to the movement of galaxies. Pulsars in binary orbits lose energy exactly as expected from gravitational radiation. Gravitational lensing by clusters of galaxies matches the predictions of spacetime curvature. The expansion history of the universe, inferred from distant supernovae and the cosmic microwave background, is described by relativistic cosmology, and yet, baked into the equations is a kind of warning label. Under certain conditions, the geometry they describe develops singularities. When enough mass is compressed into a small enough region, there is no way to avoid the formation of an event horizon, and, inside it, a region where the curvature grows without bound. General relativity does not tell us what actually exists there. It only tells us that its own description stops being meaningful. Einstein himself resisted the idea that such objects might be real. The earliest solutions that looked like black holes were treated as mathematical curiosities. But as work by people like Oppenheimer, Snyder, and later Penrose sharpened the picture, it became harder to escape the conclusion that collapsing stars and dense regions of the universe would naturally form horizons. Gravity, when pushed to the extreme in its geometric form, seems to end in places where the map tears. This is the paradox that waits at the end of Einstein's radical turn. He gave us a view of gravity that is deeper and more coherent than Newton's. One in which the fall of a stone, the orbit of Mercury, and the bending of starlight are all expressions of a single, curved geometry. He also gave us a theory that, taken seriously, points beyond itself. Singularities, horizons, and the strange behavior of time near them signal that general relativity, for all its beauty, is incomplete. We now know that there is another domain where Einstein's gravity does not yet speak fluently: the quantum world. At very small scales, particles and fields do not behave like continuous matter on a smooth stage. They flicker, fluctuate, and obey a different set of rules. Quantum field theory and general relativity are both successful in their own realms, but when we try to combine them, their languages clash. This is where gravity's mystery deepens again. If spacetime is curved, does it also come in quanta? Is there a smallest unit of area or volume? Is there a particle, a graviton, that carries the gravitational interaction, the way photons carry electromagnetism? Or is gravity not a fundamental force at all, but a collective effect emerging from an even deeper layer of reality? These questions belong to later chapters. What matters here is that the shift from force to geometry was not the end of the story. It was the beginning of a new kind of puzzle. Einstein turned gravity into the architecture of the universe. In doing so, he made it possible to see more clearly where that architecture cracks. The straightest path of a falling stone now passes through a landscape that, at its limits, may require an entirely new way of thinking. Somewhere between the kitchen floor where a glass shatters and the dark edge of a black hole where time twists, gravity has transformed from a familiar tug into a clue. A clue that the stage on which we live is not fixed. A clue that even the flow of time is negotiable. A clue that whatever reality is at its deepest, we are still only tracing its outline by watching how it bends the paths of things that fall. If gravity is the shape of the stage, then singularities are the places where the stage seems to tear, where the script continues, but the paper runs out. To follow gravity honestly, we eventually have to walk right up to those edges and admit that the map in our hands stops there. Begin with something deceptively simple. A star that has burned through almost all of its fuel. For millions or billions of years, it has lived in a kind of delicate truce. On the inside, nuclear reactions push outward, heating gas and light and particles that want to expand. On the outside, gravity pulls inward, trying to make the star smaller. For a long time, those two tendencies almost cancel. A star is what you get when outward pressure and inward gravity hold each other in a shifting, dynamic balance. But no star has infinite fuel. When the nuclear reactions that support it weaken and stop, the balance fails. Gravity does not get tired. It does not need to be replenished. If nothing else steps in to resist, the star begins to collapse under its own weight. Matter falls toward the center. Layers crush those beneath them. Densities rise. For small stars, nature has emergency brakes. Quantum mechanics sets up new kinds of pressure from electrons or neutrons that refuse to be squeezed too close together. White dwarfs and neutron stars are what remain when those brakes are strong enough to stop collapse. But push the mass high enough, and even those quantum pressures lose the fight. At that point, according to Einstein's equations, there is nothing in the known catalog of matter that can resist gravity. The collapse continues. In the late 1930s, J. Robert Oppenheimer and Hartland Snyder did something that, at the time, seemed theoretical and remote. They wrote down an idealized model of a massive star collapsing in on itself, and they followed the equations of general relativity all the way inward. Their calculations suggested that, from the point of view of an outside observer, the star's surface would appear to freeze, redshift, and fade as it approached a certain boundary. From the point of view of someone riding with the collapsing matter, however, there was no freeze. The surface crossed a point of no return and kept going. That point of no return is what we now call an event horizon. Once something passes inside, every future path it could take leads deeper toward the center. No path leads back out to the wider universe. Not even light can escape. The region inside is cut off, causally sealed. For a long time, physicists were unsure whether this was a trick of the coordinates, a mathematical artifact, or a description of something real. The word black hole had not yet been coined, and the idea of an object from which nothing could escape did not sit easily with the physical imagination. Even if you accept the existence of an event horizon, you can ask a further question. What happens at the center, after the collapse has gone on, as far as it can? In Oppenheimer and Snyder's idealized picture, and in many simple solutions to Einstein's equations, the answer is brutal in its simplicity. The matter contracts toward a singularity, a region where densities and curvatures in the mathematics grow without bound. Not merely very large, but formally infinite. Here, the language gets treacherous. Infinity in an equation does not necessarily mean there is a physical point in space with literally infinite density or curvature. It means the theory, as written, is returning a signal that says, in effect, I cannot continue this description. The variables I use have reached a place where they no longer track anything meaningful. The singularity is less like a concrete object and more like a red warning light on the dashboard of general relativity. It tells you that, if you want to talk about what really happens there, you probably need a different theory. For a while, you might hope that such pathological situations only appear in special, highly symmetric models. Maybe, one could imagine, realistic stars with irregularities and rotations never quite form singularities. Maybe the universe conspires to avoid those infinities in practice, even if the simplest equations suggest them. In 1965, Roger Penrose took that hope away, or at least narrowed it severely. Using a new set of mathematical tools involving geodesics, causal structure, and what he called trapped surfaces, he proved a general theorem. If certain reasonable conditions hold in a spacetime, and if a region exists where light rays are forced to converge in a particular way, then the formation of singularities is unavoidable within general relativity. You do not need perfect symmetry. You do not need special initial conditions. Collapse beyond a certain threshold leads to a breakdown of the theory's description. This was a turning point. It said that singularities are not rare glitches or artifacts of idealization. They are woven into the fabric of the theory whenever gravity is strong enough and focused enough. Black holes are not curiosities. They are robust predictions. Later work extended similar reasoning to the whole universe, suggesting that if you follow the expansion of the cosmos backwards in time under certain conditions, you encounter a singular origin, A singularity, in this sense, is not a point marked on a map like a mountain or a crater. It is the failure of the map itself. In some directions, you can extend paths indefinitely. In others, you cannot. A geodesic, which in general relativity is the path of a freely falling object or light ray, ends after a finite amount of proper time or affine parameter. There is no way to say what lies beyond, because the theory does not supply any continuation. This realization led to another worry. If singularities can form, do they always hide behind event horizons, as in the black hole story? Or can they sometimes sit naked in the universe, exposed to distant observers? A naked singularity would be an open wound in predictability. In its neighborhood, the ability to forecast future events from present data would break down. Cause and effect would be ill-defined in a way that infects the wider cosmos. To preserve some sense of order, Penrose proposed an idea known as cosmic censorship. In its weak form, it suggests that, in physically reasonable situations, singularities produced by gravitational collapse are always clothed by horizons. The truly wild behavior of space-time remains quarantined behind a one-way boundary. The rest of the universe sees only the external face of the black hole, the curvature outside the horizon, not the breakdown of the map inside. Cosmic censorship is a conjecture, not a proven theorem. Physicists have constructed mathematical examples where naked singularities appear, often by dialing in special initial conditions or exotic matter. Numerical simulations have probed situations in which collapse leads to borderline outcomes, delicately balanced between horizon formation and exposure. The general question remains open: does nature enforce censorship? Or does it allow occasional flashes of raw, singular behavior to touch the wider universe? Meanwhile, work on the interior structure of singularities revealed that they are not all the same. In the 1960s and 1970s, Belinsky, Kolotnikov, and Lifshitz proposed a picture in which, near a generic space-like singularity, the geometry of space-time undergoes a chaotic sequence of oscillations. Instead of a smooth approach to a simple point, the metric components bounce and twist in a way that is sometimes described as a mixmaster, after a brand of kitchen appliance. Local regions decouple from each other and follow their own violent dance toward the edge. Later, in the 1990s and beyond, numerical relativists used computers to simulate gravitational collapse and cosmological models with increasing detail. They found support for some aspects of this chaotic approach in certain settings, and more intricate behavior in others. The overall picture that emerged is one in which singularities, instead of being neat points or lines, are complicated regions where the curvature grows wildly and the usual notions of space and time dissolve. Despite this internal complexity, the external appearance of a black hole is, in many ways, simple. From the outside, it can be described by a few parameters: its mass, its spin, its charge, if any. Details of the matter that fell in are erased. This led to the saying that black holes have no hair. All the rich, messy information about what collapsed to form them is lost behind the horizon. At least in classical general relativity, there is a peculiar contrast here. Inside, near the singularity, the geometry is complicated and violent. Outside, the gravitational field can be described by clean, symmetric solutions like the Schwarzschild or Kerr metrics. From a distance, a black hole is as serene and featureless as a dark, perfectly round lake. Up close, at least according to the equations, space-time itself is shredding. Our visual culture has started to catch up with these ideas. When the film Interstellar needed an image of a spinning black hole, the team contacted physicist Kip Thorne and used actual relativity equations to compute how light would bend around a rotating horizon and its surrounding disk of matter. The result? A luminous ring warped above and below a dark center, looked unfamiliar yet plausible. It was not a swirling drain or a simple black circle, but a distorted lens created by intense curvature. Years later, the Event Horizon Telescope collaboration stitched together radio observations from multiple continents to produce the first image of the shadow of a supermassive black hole in another galaxy. The resolution was limited. The ring was blurry and uneven, but there it was, a dark center where the horizon's shadow falls on the backdrop of glowing gas, surrounded by a bright, lopsided ring of light. A direct observation of space-time geometry strong enough to trap light. These images do not show singularities. They show horizons, the surfaces beyond which the singular interior is hidden. The singularity itself remains off-screen. Not because we lack powerful enough telescopes, but because, in principle, no light from that region can reach us. The map ends there, behind a boundary that is one way only. At this point, it is tempting to ask whether singularities are real things in the world, or just signs that our equations are incomplete. Many physicists lean toward the second view. They expect that a complete theory of quantum gravity, whatever form it takes, will smooth out the infinities, replacing the singular region with some finite structure, perhaps involving discrete chunks of space-time or new degrees of freedom. But even if that hope is fulfilled, the singularities of classical general relativity retain their importance. They tell us where the classical theory cannot be trusted. They tell us that gravity, when pushed hard enough, demands a quantum description. They mark a boundary in our understanding. And they do so with mathematical clarity. You can prove that, under certain conditions, your theory predicts its own demise. There is another way to see singularities, less technical and more reflective. On old maps of the world, unexplored regions were sometimes labeled with phrases like, "Here be dragons." The cartographers were not claiming that literal dragons existed. They were admitting that beyond the line, their knowledge ended and imagination took over. In a sense, singularities are the "here be dragons" of Einstein's map. Not beasts, but blankness. The difference is that in geography, explorers can sail beyond the edge and correct the map. In the case of black hole interiors, or the supposed initial singularity of the universe, we cannot simply build a ship and go look. The horizons and the structure of space-time itself prevent direct observation. Any story we tell about what happens beyond the classical singularity relies on extending or replacing the theory. Guided by consistency, by indirect clues, by mathematical beauty, by whatever experimental scraps we can gather. That limitation can feel frustrating. We are used to thinking of science as a steady march toward complete knowledge. Singularities remind us that our best theories can be honest enough to mark their own limits. They say, "Here, our language breaks. Here, our concepts do not apply. Here, you must either invent new ones or accept that some questions, framed in the old language, cannot even be asked properly." There is an existential echo in this. Humans often meet their own limits, not in the middle of ordinary days, but at extremes. In great loss, in overwhelming beauty, in moments of crisis or awe. The mind that is usually so good at naming and organizing suddenly runs out of words. Singularities are where the universe's current physical story runs out of words. Gravity, by focusing matter and bending time, creates places where our ideas about space and time cannot follow. And yet, those very failures are productive. The singularity theorems of Penrose and others did not shut down inquiry. They sparked entire research programs in quantum gravity, in numerical relativity, in cosmology. The recognition that general relativity predicts its own breakdown did not kill the theory. It clarified its domain. It made its successes more meaningful and its gaps more visible. You might think of gravity's map as having two kinds of regions. There are areas where the geometry is gentle enough that our current equations work beautifully, from planetary orbits to gravitational lensing to the subtle drift of satellite clocks. And there are areas where the geometry becomes so extreme that those same equations signal their own inadequacy. Singularities live in that second region. They are the edge, where the known and the unknown meet. Standing at that edge, at least in imagination, changes how we think about the rest of the map. A black hole forming from a collapsing star is not just an exotic object in a distant galaxy. It is a demonstration that the same gravity pulling on the stone in your hand can, under different conditions, create a region where time and space lose their usual meanings. An expanding universe that might trace back to a singular beginning is not just a cosmological model. It is an invitation to rethink what we mean by origin. In that sense, singularities do not only belong to astrophysics or mathematical relativity. They belong to our evolving understanding of explanation itself. If the deepest theory we have says, with precise theorems, that it cannot describe certain regions, then any future theory will have to do more than add new particles or tweak equations. It will have to teach us a new way to talk about locality, causality, and perhaps about space and time themselves. The mystery of gravity, viewed from this angle, is not only that it pulls, or even that it bends. It is that, when concentrated, it creates its own horizons. It builds regions where information seems to disappear and where the flow of time is caught in a trap. At the center of those traps, the classical description ends in a singularity. Whether quantum gravity replaces that with something tame or something even stranger, the message from Einstein's map is clear. To understand gravity fully, we have to follow it all the way to the places where, for now, it stops talking. If singularities are the places where the old story breaks, then quantum gravity is the suspicion that the paper of space-time itself is made of smaller fibers. Somewhere beneath the smooth curves and continuous time, we expect to find quanta. By the time Einstein's theory had settled into textbooks, physics had already undergone a different kind of revolution. The other three forces we know about were slowly being rewritten in quantum language. Electricity and magnetism merged into a single electromagnetic field. The strong and weak nuclear forces joined that family in the framework of quantum field theory. In that language, what we call a force is not a mysterious pull, but the exchange of particles. Photons carry electromagnetic influence. Gluons carry the strong force. The weak force has its own heavy carriers. In that picture, fields fill space, and particles are the smallest ripples of those fields. A single photon is the smallest packet, or quantum, of the electromagnetic field. When light grows brighter, we do not imagine a continuous shine becoming thicker. We imagine more and more photons, like drops in a rain, increasing. Even if you dim the light down to almost nothing, you can still, in principle, speak of individual quanta clicking in a detector, each one a tiny, clear event. Gravity, in contrast, has remained stubbornly classical in our best working theory. General relativity treats space-time as a smooth, continuous geometry. Curvature is not grainy. There is no obvious smallest bend. Yet, if all the other fields have quanta, it is natural to suspect that gravity does too, that space-time itself has a quantum description. In that description, there should be a particle that plays for gravity, the same role the photon plays for electromagnetism. That hypothetical particle is called the graviton. In the simplest view, it would be massless, like the photon, traveling at the speed of light. It would carry spin too, meaning that, if you rotate your coordinate system, its internal pattern looks the same only after a half turn, not a full one. These properties are not arbitrary. They are what you get if you quantize small ripples in a field whose classical limit looks like a metric. The object that defines distances and times. Many different approaches to quantum gravity, even ones that disagree on almost everything else, contain something like a graviton. In string theory, gravity emerges naturally when you allow vibrating strings to move in a way that includes a massless spin to excitation. In loop quantum gravity, the fundamental objects are more geometric, involving discrete spectra of area and volume. But in suitable limits, the theory is expected to reproduce a graviton description for weak gravitational waves. In effective field theory, you can treat general relativity as the low-energy approximation of some deeper, unknown theory, and still talk meaningfully about gravitons at energies where the theory makes sense. Gravitons, then, are less an exotic fantasy and more a natural expectation if you believe that the world is quantum all the way down. The question is not so much whether a quantum of gravity can be written in an equation, but whether it can ever be touched by an experiment. On September 14, 2015, a pair of long, L-shaped instruments in Louisiana and Washington recorded a pattern that looked, at first, like noise. The Laser Interferometer Gravitational Wave Observatory had been listening for changes in the lengths of its arms, so tiny that they could be described in fractions of a proton's size. Changes caused by passing gravitational waves. The signal they eventually identified came from two black holes spiraling together and merging more than 1 billion light-years away. Space-time itself had rung like a bell, and that ringing had crossed the universe to nudge mirrors on Earth by less than the width of an atomic nucleus. The announcement, made the following year, was framed as the detection of gravitational waves, and rightly so. But if you lean closer, a quieter implication appears. If gravitational waves exist and carry energy, and if the world is fundamentally quantum, then those waves must be composed of an enormous number of gravitons, just as a laser beam is composed of many photons. The L-shaped detectors had not seen individual quanta. They had measured a collective vibration, a flood. The dream that hangs over this, like a distant star, is to push even further. To detect not waves composed of unimaginable numbers of gravitons, but a single graviton itself. To see one discrete quantum of the gravitational field triggering a specific response in a detector, or to produce gravitons in high-energy collisions and infer their presence from missing energy and momentum, as we do with neutrinos or other elusive particles. There are two broad routes you might imagine for such a task. One is to build a detector so sensitive that the passage of a single graviton would leave a measurable imprint. The other is to create conditions in a particle collider, where gravitons are emitted in significant numbers, and to design experiments that can infer their existence from statistical patterns. Consider the first route. A detector for single gravitons would have to be fantastically delicate. A gravitational wave that LIGO can detect corresponds not to a few quanta, but to an enormous number. To reduce that down to a single graviton's effect, the necessary sensitivity explodes. The displacement you would need to measure in a mirror, or in a quantum system standing in for a mirror, becomes so small that it approaches the Planck length. The tiny scale, built from fundamental constants of gravity, quantum mechanics, and the speed of light. At that scale, quantum uncertainty becomes a dominant obstacle. To know the position of a mirror with that precision, you would have to probe it with extremely energetic photons. But the more energetic the photons, the more violently they kick the mirror, blurring its momentum and ruining the very measurement you are trying to perform. The improvement gained in one variable is lost in another. You cannot both localize and leave untouched. You might then try to solve this by making the detector more massive so that the kicks from probing photons have less effect. But if you concentrate enough mass into a small enough region, general relativity speaks up. The energy density becomes high enough to form a black hole. Instead of detecting gravitons, your detector would collapse into the very kind of object whose interior you cannot observe. The universe, in this imagined experiment, protects its secrets with its own rules. Push too hard, and the stage tears around your apparatus. The second route uses colliders. The Large Hadron Collider near Geneva already accelerates protons to energies unprecedented in a laboratory and smashes them together. In some models with extra dimensions or other extensions of known physics, high-energy collisions could, in principle, emit gravitons into the larger space-time or into hidden dimensions. They would not be seen directly, but their escape would show up as missing energy and momentum in the debris of the collision. Experiments have looked for such patterns and, so far, have found none that require gravitons. They have instead placed limits on how strongly gravity could couple in such scenarios. More fundamentally, even if you did see a signal consistent with gravitons, the probability that any one of them interacts with your detectors is extremely tiny. Gravity is far weaker than the other forces at the scales we can reach. The cross-sections, the effective sizes of the targets for gravitons to hit, are minuscule. You can flood a detector with a storm of hypothetical gravitons and still expect almost none of them to register. In 2012, at a meeting in Aalborg, Denmark, The physicist Freeman Dyson gave a talk with a deliberately modest but unsettling question in the title. Is a graviton detectable? He did not doubt that a quantum theory of gravity exists in some form. His challenge was whether the quanta of that theory, gravitons, could ever be observed in any experiment allowed by the laws of physics and the resources of the observable universe. His analysis, and others like it, suggested a disturbing possibility. The attempts to build graviton detectors either run into quantum limits that destroy the measurement or into gravitational collapse that destroys the detector. The attempts to use colliders are thwarted by the extreme weakness of gravity at accessible energies. Even clever schemes involving astrophysical sources and indirect effects fall afoul of overwhelming backgrounds and vanishingly small probabilities. From this, Dyson drew a line between what is real and what is observable. A graviton could be as real, in the theoretical sense, as a photon. It could be part of a correct description of the quantum structure of space-time, and yet it might never be isolated, never be seen as a discrete event in a detector. The universe might contain a perfectly good quantum gravity theory and still deny us any direct experimental handle on its basic quanta. This thought brushes against the philosophy of science. We usually define physics as the part of our thought that can, in principle, be tested. Even if an experiment is difficult or expensive, as long as it is possible in some ideal limit, we feel on solid ground. But what if there are aspects of reality that are permanently shielded by the very laws we are trying to uncover? What if the attempt to design an experiment that touches them always triggers the formation of a black hole, or the boiling of the quantum vacuum, or some other self-protective response of the cosmos? In that case, the hunt for the graviton becomes something more ambiguous. It is not just a technical challenge, it is a probe of the boundary between what is knowable and what is not, at least by creatures like us, in a universe like ours. Gravitational waves, which we can now detect regularly, are like the music of space-time played in thick chords. A single graviton would be a single note. Perhaps the instrument we live in never lets individual notes emerge. This does not make the search pointless. Even if individual gravitons cannot be captured, their existence leaves fingerprints. The way gravitational waves behave at very high frequencies, the possible imprints of quantum gravity in the polarization of the cosmic microwave background, the subtle corrections to black hole evaporation, all of these are places where quantum gravity might leak into observable phenomena. In those leaks, the reality of gravitons and related structures could be inferred, if not directly seen. There is also a more human aspect to this. The idea that there is a smallest packet of the gravitational field fits neatly with our sense of pattern. It resonates with the story of photons, of quanta of matter fields, of the discreteness that quantum mechanics keeps revealing. To give up on gravitons entirely feels like giving up on the idea that gravity belongs fully to the same quantum world. To believe in them, even if they are forever beyond direct detection, is to insist that gravity is not exempt from the rules that govern everything else. On the other hand, some approaches to quantum gravity suggest that the graviton is not fundamental, but a convenient way of talking about small ripples on a deeper structure. In emergent gravity pictures, the basic ingredients are not fields in space-time, but bits of information, entanglement patterns, or other pre-geometric entities. In that view, a graviton is like a phonon in a crystal, a collective vibration that has meaning only at scales much larger than the fundamental lattice. Whether the graviton is a truly fundamental particle or an emergent quasi-particle, whether it can ever be singled out in an experiment or only inferred from collective behavior, the very act of considering it changes how we see space-time. No longer is the gravitational field a smooth, infinitely divisible medium. It becomes, at least in imagination, something that might come in grains. There is a quiet irony in this too. Gravity feels continuous in our bodies. We do not experience it as a series of tiny jolts. We experience it as a persistent pressure, a constant downward pull. And yet, the quest to understand it at the deepest level leads us to imagine single quanta flickering in and out, exchanging momentum with particles, propagating across the cosmos in unimaginably delicate ways. Stand back, and you can see a pattern emerging from this chapter and the previous ones. Singularities told us that classical space-time breaks. The graviton tells us that, even where space-time seems smooth, it might be woven from quantum threads. General relativity gave us a continuous stage. Quantum gravity hints that the stage is built from pieces. The hunt for the graviton, whether successful or forever thwarted, is the way we ask the universe whether that suspicion is true. In the chapters ahead, we will see other ways of asking the same question. Some imagine that gravity hides its quanta so well that no experiment can find them. Others suggest that gravity itself is not fundamental, but arises from entropy and information, making the graviton a secondary character. Still others explore the possibility that gravity leaks into dimensions we cannot see, weakening it in our world. All of them are, in their own language, ways of listening for a quantum echo in the most familiar and most mysterious of forces. If the graviton is a single note in the music of space-time, Dyson's question is disarmingly simple. Can any instrument in this universe ever hear that note on its own? To see why this is not just a technical curiosity, it helps to go back to a very concrete scene. Imagine one of the long, silent halls of the gravitational wave observatories on Earth. In Louisiana and Washington, two immense L-shaped machines stretch their arms for roughly 4 kilometers in each direction. Inside evacuated tubes, laser light bounces back and forth between mirrors, tracing the distance so precisely that a passing gravitational wave can be felt as a change far smaller than the diameter of an atomic nucleus. On September 14, 2015, those mirrors shifted by an amount that, in ordinary language, is essentially nothing. And yet, from that almost nothing, physicists reconstructed the story of two black holes spiraling together more than 1 billion light-years away. They heard space-time ring. The discovery was celebrated as a triumph of patience, engineering, and Einstein's equations. But if a gravitational wave, that strong, from an event that violent, moves the mirrors by so little, what would a single graviton do? A gravitational wave, in a quantum picture, is an enormous crowd of gravitons moving in step. The wave LIGO heard contained a number of quanta that can be written as 10 to the power of something like 36, an almost incomprehensible swarm. The disturbance from just one member of that swarm would be correspondingly tiny. You can phrase the thought experiment like this. Take the existing detector and imagine turning down the volume of the incoming wave until only one graviton remains. The effect on the mirrors now is essentially nothing, not in the casual sense, but in the literal sense that the displacement is beneath the noise imposed by quantum mechanics itself. To pick out that single quantum, you would need a detector whose sensitivity is greater by roughly that huge factor. That is, more sensitive by many orders of magnitude beyond what we already consider extraordinary. At some point, this is no longer a matter of building a better vacuum system or polishing the mirrors more carefully. It becomes a matter of confronting the quantum nature of the measuring device. To know the position of a mirror to fantastically high precision, you must probe it with light of extremely short wavelength, and therefore high energy. Those high-energy photons kick the mirror every time they bounce, giving it random momentum. The more exactly you measure the position, the more uncertain the momentum becomes. The mirror jitters. There is a limit, set by the Heisenberg uncertainty principle. You cannot know both quantities arbitrarily well at the same time. Engineers and physicists already live with this limitation. They design clever schemes to squeeze quantum noise, to arrange the light in special states that reduce fluctuations in one variable at the cost of increasing them in another. That is how gravitational wave detectors have improved beyond their initial designs. But when you ask for a sensitivity good enough to detect a single graviton, even the most optimistic versions of these tricks fail. The very act of measurement shakes the detector more than the signal you hope to see. You might then imagine changing the strategy. Instead of making the measurement more delicate, make the measuring device heavier. If the mirrors have more mass, the same kicks from probing photons will produce smaller jitters. With enough mass, perhaps the mirror's position can be known to the required precision without being disturbed too much. This line of thought runs headlong into gravity itself. When you pack enough mass into a small enough volume, general relativity says that you form a black hole. There is a radius, called the Schwarzschild radius, inside which the escape speed exceeds the speed of light. If your mirror and its supporting structure are compressed below that threshold, they disappear behind an event horizon. Your exquisitely designed graviton detector becomes, quite literally, the very sort of object whose interior is cut off from outside communication. Dyson and others played this game of imaginative construction and destruction with some care. They varied the shape and size of the detector, the way it couples to the gravitational field, the energy of the probing light. The patterns repeated. When you tried to beat the quantum limits, gravity would intervene and make the apparatus collapse. When you tried to avoid collapse by spreading things out, the signal became too weak to detect over the background noise. The universe, it seemed, was not just making it difficult to see a graviton. It was closing every path. If direct detection in a LIGO-like setup seemed impossible, the next natural thought was to look to particle colliders. Perhaps, instead of waiting for gravitons from distant astrophysical events, we could create them on demand, accelerate particles to enormous energies, collide them, and let the gravitational field participate. The graviton, if it exists as a particle in the quantum sense, should be able to be emitted in such a high-energy process. We already use this logic with other elusive particles. Neutrinos, for example, barely interact with matter. They pass through entire planets with ease. We do not see them directly in most experiments. We infer their presence from missing energy and momentum in collisions. Could the same be done with gravitons? The difficulty is again a matter of scale. Gravity is incredibly weak compared to the other forces at distances and energies we can access. The strength of an interaction in a collider can be estimated by a cross-section, a quantity that effectively measures the size of the target the incoming particle presents. For gravitons, at realistic energies, this cross-section is so small that even if your collider produced oceans of them, almost none would leave any trace in your detectors. They would slip through the apparatus and out into space as if it were almost perfectly transparent. To change this, you would need to increase the energy to such high levels that the gravitational coupling becomes stronger. That means a collider with a ring so large that its radius might be measured in light years. It means magnetic fields of strengths that push against the structural limits of matter. It means energy densities that, again, invite gravitational collapse. The imagined machine begins to look less like a practical proposal and more like a thought experiment that shows how the universe forbids certain direct questions. There is a third route that might occur to a determined experimenter. If we cannot easily produce or catch gravitons in human-made devices, perhaps we can borrow what nature already does. Stars, white dwarfs, neutron stars, and black hole mergers all flood space with gravitational radiation. Maybe, somewhere in that reign of quanta, there is a way to let a single graviton reveal itself. Here, too, detailed calculations cut the hope down. If you estimate the flux of gravitons from the Sun, for instance, and the probability that any one of them would interact with a detector on Earth, you arrive at an absurdly low number. Over the entire lifetime of our planet, it is extraordinarily unlikely that even a single graviton would leave an unmistakable mark in any realistic detector volume. The situation is no better if you look at more exotic sources. The universe might be filled with gravitational quanta, but the terms on which they interact with matter are so gentle that they pass by unnoticed. Some proposals try to sidestep this by using the Gertsenstein effect, an idea dating back to the 1960s. In a strong magnetic field, a gravitational wave can, in principle, convert into an electromagnetic wave, and vice versa. That is, a graviton moving through a magnetized region could become a photon, which is much easier to detect. Now, the problem looks like a communications issue between two languages of nature: gravity and electromagnetism. The proposed experiment is simple in spirit and daunting in detail. Build a very long tube, create an extremely strong magnetic field inside it, and aim it at a source of gravitational waves. Wait for some of those waves to convert into photons as they pass through. Catch those photons at the far end with a sensitive detector. If you see a signal with the right properties, you can argue that it came from gravitons translated into light. The stumbling block, yet again, is in the numbers. The conversion probability is minuscule. To raise it to a decent level, you need magnetic fields far beyond what current materials can handle. At some point, the vacuum itself becomes unstable. Quantum field theory says that a strong enough field will cause the vacuum to sprout particle-antiparticle pairs, a kind of boiling that drains energy and disturbs coherence. The neat, reversible conversion you hoped for is spoiled by the very quantum fluctuations you are trying to exploit. After surveying these options, Dyson suggested a stark conclusion. It may be that, in any universe governed by something like our known laws, with gravity as weak as it is, and quantum mechanics as strict as it is, no experiment can ever detect a single graviton. Gravitons can exist in the sense that they are part of an overwhelmingly well-motivated theory. They can participate in the internal bookkeeping of quantum gravity calculations. They can even play a role in the thermodynamics of black holes and the early universe. But they may be forever beyond the reach of direct observation. This does not mean that quantum gravity itself is beyond science. We can still test the consequences of different quantum gravity proposals in indirect ways. We can look for deviations from the predictions of classical general relativity in extreme environments, for tiny imprints in the cosmic microwave background, for modified dispersion of gravitational waves, for corrections to the evaporation of black holes. The space of possibilities there is rich. What Dyson's argument touches, however, is a deeper anxiety, that there may be parts of reality that are forever outside the reach of experiment, not because we lack imagination or funding, but because the laws themselves guard them. The universe here is not just a stage where everything that can happen does. It is a structure with built-in limits on what can be known by embodied observers like us, building finite machines from ordinary matter. We have met limits before in physics. The speed of light is a limit on how fast information can travel. The uncertainty principle is a limit on how precisely certain pairs of quantities can be known at once. The second law of thermodynamics is a limit on how much useful work can be extracted and how completely processes can be reversed. Dyson's impossibility arguments suggest a new kind of limit, a cap on how directly we can probe the quantum grain of space-time itself. There is a certain symmetry to this. Gravity, from the beginning of this story, has been the force that, more than any other, blurs distinctions between here and there, between now and later. It ties the motion of a falling stone to the geometry of the cosmos. It allows dense regions to hide behind horizons. It shapes the global structure of the universe, using a local law. It is somehow fitting that, when we try to press it into the same experimental mold as other forces, it slips away. You could respond to Dyson's conclusion in several ways. One is to take it as a challenge. Maybe there is a clever idea no one has thought of yet. An arrangement of quantum systems, or a use of entanglement, or an exploitation of some new regime of materials that evades the arguments and captures a graviton's whisper. The history of physics is full of problems that seemed impossible until someone reframed them. Another response is more philosophical. Perhaps we can accept that certain entities in our theories are, in principle, unobservable as isolated objects, and still count the theories as physical as long as they have other testable consequences. We already do this, to some extent, with things like virtual particles in quantum field theory. They are not particles in the naive sense, not directly observable events, but they contribute to measurable quantities, like energy levels and scattering amplitudes. In that view, gravitons might be similar. We would never see a single graviton strike a detector, but we could measure effects that only make sense if something like gravitons exist in the deeper bookkeeping. The reality of the particle would be inferential rather than direct. This is less satisfying emotionally, but not necessarily less scientific. A third response is to question whether the graviton, as a particle, is the right focus at all. If gravity is emergent, if space-time geometry arises from more fundamental degrees of freedom, like entanglement or information, then the graviton might be akin to a sound wave in air. You can talk about phonons, quanta of sound, and they are useful, but they are not fundamental in the way atoms are. If you built a detector to capture a single phonon, you would not be probing the deepest layer of reality, only a collective mode. In that picture, the impossibility of detecting a graviton directly might be less disturbing. It could simply mean that we are trying to touch an emergent object with the wrong expectations. The real action would be elsewhere, in the microstructure that gives rise to geometry, not in the ripples of geometry itself. Whichever stance you take, Dyson's arguments leave an aftertaste. They remind us that the universe is not obligated to make every reasonable question experimentally accessible. We can ask whether gravitons exist as quanta of the gravitational field. Our theories can answer, in the language of mathematics, that they do. But the universe can answer, in the language of constraints, that we will never catch one. There is a quiet, unsettling beauty in that situation. It forces us to confront the fact that knowledge is always shaped by the conditions of the knower. Our tools are made of matter that obeys the same laws we are trying to uncover. Our detectors fall under gravity, fluctuate under quantum rules, radiate heat. We cannot step outside of physics to study physics. We are part of the system we measure. Gravity, in particular, makes that entanglement between knower and known explicit. Any attempt to build a graviton detector that is too ambitious becomes a gravitational object in its own right. Any attempt to isolate the tiniest bend in spacetime runs into the way spacetime responds to energy. The universe, through gravity, pushes back. Seen from that angle, Dyson's impossibility arguments are not a dead end, but a mirror. They show us not just what we cannot do, but what kind of beings we are in this cosmos. Local, finite, made of the same fields and particles we study, subject to the same limits we write in our equations. Gravity has always been the most intimate of forces, felt in the soles of our feet and in the orbits of planets. In hiding its own quantum particle from us, it adds another layer to that intimacy. It reminds us that some mysteries are not mistakes waiting to be corrected, but features of a universe in which explanation itself has an edge. If gravity limits what we can know at the smallest scales, it also confronts us with a different kind of ignorance at the largest ones. Even where the equations work beautifully, the sky sometimes answers with motions that do not add up. Imagine standing on the deck of a ship, looking out at a vast carousel of distant lights. A spiral galaxy, seen from outside, is just that. A flat disk of stars, gas, and dust, slowly turning like a luminous whirlpool. Near the center, stars crowd together. Farther out, the spiral arms thin into delicate threads. Intuition suggests that the stars near the middle, deeper in the gravitational well, should race around faster, while those at the edge should move more slowly, like the outer seats of a merry-go-round that lag behind. In the middle of the 20th century, astronomers started to measure these motions with care. They mapped how fast gas and stars orbit at different distances from a galaxy's center. The tool was simple in principle. Light shifts in frequency when objects move toward or away from us. A cosmic Doppler effect. From that shift, you infer speed. Put those speeds on a graph, radius against rotation, and you get what is called a rotation curve. The expectation from Newton and Einstein is straightforward. Inside a certain radius, where the mass increases as you include more of the galaxy, speeds can rise. But beyond that, where most of the mass is inside your orbit, the speeds should fall, curving downward like a stone thrown upward that slows as it climbs. The gravitational pull from the visible matter, stars and gas, should not be strong enough to keep outer stars moving very fast without flinging them out of the galaxy altogether. What the data showed, again and again, was different. The rotation curves rose and then stayed flat. Stars far out in the disk were orbiting almost as fast as those closer in. It was as if the galaxy was surrounded by a massive, invisible halo, adding gravity where there was no light. This was not a small mismatch. It was a systematic pattern across many galaxies. The most straightforward way to rescue Newton and Einstein was to accept that there is more mass than we can see. Call it dark matter. It does not emit or absorb light, at least not in ways we can easily detect, but it gravitates. Wrap each galaxy in a halo of this unseen matter, extending far beyond the visible disk, and the flat rotation curves make sense. The extra mass keeps outer stars bound and moving fast. Over time, the dark matter idea grew into a larger framework. It helped explain not only how individual galaxies rotate, but how galaxies cluster together, how large-scale structures form in the universe, how the cosmic microwave background shows tiny temperature ripples that grow into cosmic web patterns. A self-consistent picture emerged in which most of the matter in the universe is dark, some form of non-luminous, weakly interacting particles. Ordinary atoms, the stuff of stars and people, are a minority. But from the beginning, there was another way to read the same data. Instead of adding new matter, you could ask whether the law of gravity itself changes in the regime of extremely small accelerations. The kinds of gentle pulls that dominate at the edges of galaxies. Maybe, in those conditions, Newton's law is only approximately right. Maybe gravity has modes of behavior, like a material that flows under some stresses and resists under others. In the early 1980s, Mordechai Milgram proposed a concrete version of this idea. He called it Modified Newtonian Dynamics, abbreviated as MOND. The central thought was simple to state and delicate to implement. There exists a characteristic acceleration scale, far smaller than what we experience on Earth. When gravitational accelerations are much larger than that scale, Newton's law holds. When they are much smaller, the effective gravitational pull falls off more slowly with distance than Newton predicts. In practice, this means that in the faint outer parts of galaxies, where the acceleration a star feels is tiny, gravity refuses to weaken as quickly as expected. The result is nearly flat rotation curves, just as observed, without invoking invisible halos. Given the distribution of visible matter in a galaxy, MOND gives a rule to compute the orbital speeds. Astonishingly, in many cases, the rule works with surprising precision. One of the striking patterns MOND highlighted is a relation between the mass of a galaxy's visible baryonic matter and the characteristic speed of its rotation. This is sometimes called the baryonic Tully-Fisher relation. In MOND, this relation falls out naturally. The asymptotic rotation speed is tied to the fourth root of the baryonic mass, times a constant related to the characteristic acceleration scale. In the dark matter picture, the same relation must be explained by how visible matter and dark halos co-assemble and interact over cosmic time. A more complicated story. There is a psychological tension here that echoes earlier chapters. Dark matter keeps the law of gravity pristine, at the cost of filling the universe with an unseen substance that has not yet been detected directly in a laboratory, despite decades of effort. MOND keeps the matter inventory lean, at the cost of tinkering with the law itself in a way that, at first, looked ad hoc and non-relativistic. As data improved, the argument grew more intricate. Dark matter supporters pointed to galaxy clusters, where the mass needed to hold the cluster together seems far greater than what MOND predicts from visible matter alone. They pointed especially to a system nicknamed the Bullet Cluster, where two galaxy clusters have collided. The hot gas, visible in X-rays, lags behind the collision, while the inferred gravitational mass, traced by gravitational lensing of background galaxies, appears to pass through more cleanly. In the dark matter interpretation, this makes sense. Dark matter halos associated with each cluster pass through each other with little friction, while the ordinary gas collides and slows. In MOND, the situation is more troublesome. Various extensions and additions, such as including a relic neutrino population or relativistic MOND theories, have been proposed to accommodate such systems, but the fit is often strained. MOND supporters, in turn, emphasize how cleanly the theory predicts rotation curves from visible matter with few free parameters. They point to the tightness of the observed relations between baryonic mass and rotation, which, in their view, look more like modified gravity than messy baryon-dark matter interplay. They highlight small-scale challenges to the simplest dark matter models, such as the apparent paucity of satellite galaxies around some hosts, or the specific distribution of mass within dwarf galaxies. From the outside, watching this debate can feel like sitting in a courtroom where both sides have clever lawyers and the same pile of evidence. Each new observation is presented as either a blow or a vindication. A galaxy whose rotation curve matches Mond is celebrated in one camp and explained with a particular halo in the other. A cluster whose dynamics fit dark matter expectations is framed as a problem for Mond and as a natural consequence in the Standard Model. The disagreement is not just about numbers. It is about what we think a good explanation looks like. Dark matter says, "Keep gravity," as Einstein wrote it, at least on the scales we can test, and add a new component to the universe's contents. Mond says, "Keep the matter inventory modest, and accept that the law of gravity is richer and more context-dependent than we thought." Each path preserves certain intuitions and sacrifices others. There is also a difference in how settled each community feels. The dark matter picture has grown into what cosmologists call the Standard Model of cosmology, often named with Greek letters and initials. It fits a wide range of data with a set of parameters that, although not small in number, are manageable. The particle physics community has designed detectors deep underground, in space, and at colliders to search for dark matter candidates. So far, those searches have returned only limits. But the effort continues. Mond and its descendants occupy an uneasy position. They are too successful at certain galactic scales to ignore, too challenged at cluster scales, and in cosmology to accept without modification. Attempts have been made to embed Mond-like behavior into relativistic frameworks, to derive it from deeper principles, or to combine it with some form of dark component. The result is a small but persistent rebellion at the edge of mainstream gravity thinking. From the perspective of this book, what matters is not picking a winner but noticing what the existence of the debate tells us about gravity. The same gravitational law that works so well in the solar system, confirmed by spacecraft trajectories and light bending and time dilation, begins to feel less solid when stretched to galactic and cosmic scales. We can fit the data either by adding invisible mass or by bending the law. Both choices feel, in their own way, like admissions that gravity is still hiding something. There is an existential echo in this, too. Gravity, as an experience, is the most concrete of forces. We lean into it. As we walk, we rely on it to keep our bodies on the ground and our atmosphere in place. Yet when we look up and out, turning gravity into a tool to weigh galaxies and clusters, we find that our translation from felt force to cosmic arithmetic is not unique. One translation uses new matter. Another uses new rules. The difference is not visible in a falling apple. It shows up when you watch stars at the edges of spirals. Modern surveys, like those conducted with the Gaia mission, have added further layers. By measuring the positions and motions of vast numbers of stars in the Milky Way, astronomers can study how our own galaxy's mass is arranged. Analyses based on standard gravity infer a certain dark matter halo shape and density. Some Mond-inspired analyses try to fit the same motions with modified dynamics. Each side reads the same star map differently. Headlines, in this environment, tend to oscillate. When a study finds a pattern that fits Mond unexpectedly well, some articles claim that physics is wrong, that dark matter is dead, that gravity must be rewritten. When another study finds a system that seems incompatible with Mond without contortions, other headlines declare that Mond has been killed, that dark matter has triumphed. Then, in the next cycle, the roles reverse. In the background, careful work continues, less dramatic and more patient than the news. For the thoughtful listener, the lesson is subtler. Gravity is not a solved problem scaled up. It is a question that changes shape as you move from laboratory to galaxy, from galaxy to cluster, from cluster to the whole observable universe. The very fact that two such different stories can coexist, each with genuine successes and failures, is a sign that our present conceptual frame is still incomplete. Suppose, for a moment, that Mond, or something like it, turns out to be right in some limit. Gravity really does behave differently below a certain characteristic acceleration. The Standard Law is an approximation that fails in the softest regimes. What would that mean for our picture of the universe? It would suggest that we have been extrapolating too confidently from the solar system and binary pulsars to the vast, tenuous outskirts of galaxies. Our notion that one equation rules all scales would be humbled. Suppose instead that dark matter is real, that a specific particle or field is eventually detected in a laboratory, leaving no doubt that invisible mass pervades space. In that world, Mond's successes still pose a question. Why should the distributions of visible and dark matter conspire to follow such tight relations? What principle guides the assembly of galaxies so that simple Mond-like formulas often work as approximations? Even a correct theory must explain why a wrong theory works so well in some domains. In either scenario, gravity proves to be less straightforward than the smooth geometric field of general relativity, running unmodified from planet to cluster. It either shares the stage with a dominant, unseen companion, or it changes personality in gentle fields. Either way, the comfortable idea that we have already captured its essence in a single set of equations becomes harder to sustain. There is one more twist. Some lines of thought try to merge these pictures, suggesting that what we call dark matter effects might emerge from deeper properties of space-time and quantum information. In those emergent gravity ideas, Mond-like behavior arises without explicitly changing Einstein's equations or adding particles. Instead, the large-scale behavior of gravity reflects the entropic or holographic structure of the universe. We will come to this in a later chapter. For now, the Mond rebellion can be seen as a symptom rather than a destination. It is the form taken in one corner of astrophysics by a larger unease. Gravity, when used as a weighing tool, keeps giving answers that do not match the luminous matter alone. We can patch the ledger with dark entries or rewrite the accounting rules. Both are, at this stage, acts of faith supported by partial evidence. If you step out under a dark sky and imagine the Milky Way seen from outside, a thin disk of stars with a puffy halo around it, you can hold these possibilities together for a moment. Perhaps most of the galaxy's mass is in a transparent halo of exotic particles, passing through your body as you stand there, barely interacting. Perhaps instead the galaxy's graceful rotation is a hint that the law of gravity itself, the same law that shapes your weight, bends slightly in ways you cannot feel but distant stars obey. In either case, gravity remains the author of the pattern, but not yet a fully known author. The rebellion of Mond does not overturn the edifice of physics. It scratches a question mark into its margins. It reminds us that even after centuries of using gravity as our most trusted rule for motion, the universe can still surprise us on scales where no human will ever travel, but where our equations roam freely and sometimes, quietly, get lost. If changing the law of gravity feels radical, there is an even stranger possibility waiting in the wings. That gravity is not a law at all, but the way something deeper looks when we are too far away to see its parts. Think for a moment about temperature. To someone touching a warm mug, temperature feels like a basic property, as immediate as color or shape. You learn the difference between hot and cold long before you learn any physics. Yet, in the modern view, temperature is not a fundamental ingredient of the world. It is a summary. It tells you, in a single number, about the average motion of an uncountable number of molecules. When those molecules slow down, you feel cold. When they move faster, you feel warmth. Temperature emerges from motion. The same thing happened with pressure. Early thinkers imagined pressure as a kind of invisible fluid pushing outward. Only later did we learn that pressure, too, is an average story. The way molecules strike a surface and transfer momentum. You can write down equations for pressure, measure it with instruments, and use it to predict weather or design engines, all without ever mentioning molecules. But once you know about the molecules, your understanding deepens. The old laws become shadows of a finer grain. The question that follows, almost involuntarily, is whether something similar might be true of gravity. Perhaps the smooth geometry of space-time Einstein wrote down is like temperature, a coarse description of underlying microstates. Perhaps the law that relates mass and curvature is less like a fundamental commandment and more like a thermodynamic rule emerging from statistics. Hints of this idea appeared before anyone tried to turn it into a full theory. When Jacob Bekenstein and Stephen Hawking studied black holes in the 1970s, they found that horizons behave in suspiciously thermodynamic ways. A black hole has an entropy proportional to the area of its event horizon, not its volume. It has a temperature related to its surface gravity. It radiates, ever so slowly, like a hot body. The laws describing its mechanics mirror the familiar laws of thermodynamics. Entropy is, at heart, a measure of how many microscopic configurations could underlie a macroscopic state. So to say that a black hole has entropy is to hint that there are many possible micro-descriptions that all look, from the outside, like the same smooth horizon. Einstein's equations know nothing of those microstates. They deal only with geometry. Yet somehow, geometry has acquired a thermodynamic face. In the mid-1990s, Ted Jacobson took this hint seriously and flipped the logic. Instead of starting from Einstein's equations and showing that horizons behave thermodynamically, he started from the assumption that horizons have entropy and that heat flows through them. Obey the usual thermodynamic relation between heat, entropy, and temperature. From those assumptions, applied locally to all possible small horizons, he derived the Einstein field equations themselves. In other words, if you assume that space-time has a certain entropic structure and that the Clausius relation of thermodynamics holds for all local Rindler horizons, the equations that describe gravity fall out as an equation of state. Gravity becomes, in this view, a consequence of how entropy wants to behave. The curvature of spacetime is not a fundamental command. It is how the underlying microstructure responds when energy moves. This is the kind of reversal that can change how you see everything without changing a single prediction in the regimes we already understand. The motion of planets, the bending of light, gravitational waves, all those remain exactly as Einstein described. What changes is the story you tell yourself about why those equations hold. They become less like the axioms of geometry and more like the ideal gas law. Accurate, powerful, but emergent. In parallel, a different line of thought was developing in the study of quantum field theories and string theory. The anti-de Sitter/conformal field theory correspondence proposed by Juan Maldacena in the late 1990s suggested that in certain highly symmetric situations, a theory of gravity in a bulk spacetime is mathematically equivalent to a non-gravitational quantum field theory living on the boundary of that space. The bulk geometry, including its gravitational dynamics, can be read as a kind of encoded story of entanglement and interactions on the boundary. This holographic idea, named by Gerard 't Hooft and Leonard Susskind in earlier work, is radical in its implications. It says that what looks like a three-dimensional or four-dimensional world with gravity might be fully captured by a lower-dimensional theory without gravity. Volume becomes a derived concept. The interior feels real, but the fundamental description lives on the edges. In such a picture, gravity is not something you add by hand. It is what happens when you look at the boundary theory from the right perspective and translate entanglement patterns into geometry. Entanglement entropy, a measure of how quantum states are correlated across regions, maps onto the areas of minimal surfaces in the bulk. The deeper the entanglement, the more the bulk spacetime warps. In this way, geometry and quantum information intertwine. These were hints, clues that gravity might be at the same conceptual level as temperature or pressure, robust and real, yet not the deepest language available. In the year 2010, Eric Verlinde made this suspicion explicit in a proposal that went under the name entropic gravity. His suggestion was not that objects do not fall, or that we should stop using Einstein's equations. It was that the feeling of a gravitational force arises from the tendency of a system with many microscopic degrees of freedom to increase its entropy. A simple analogy helps. Imagine a polymer molecule, like a floppy chain, floating in a fluid. The molecule can bend and twist in many ways. Its entropy counts how many configurations are compatible with its endpoints. If you grab one end, and pull it away from the other, you reduce the number of configurations, and the entropy drops. When you let go, the molecule snaps back, not because there is a fundamental spring force, but because there are many more disordered configurations with the ends closer together. We describe the snapback as an entropic force. Verlinde asked whether gravity could be of this entropic type. Picture a holographic screen, an imaginary surface that stores information about the matter inside it in discrete bits. As a particle moves relative to the screen, the information associated with it changes, and so does the entropy. If nature wants to maximize entropy, there will be an effective force on the particle, pushing it in the direction that increases disorder. Under certain assumptions about how information is stored and how entropy changes with position, you can recover Newton's law of gravitation and, in more sophisticated treatments, aspects of general relativity. The details of these derivations are technical, and there is no need to trace each step. What matters for our story is the shift in attitude. Gravity is no longer assumed. It is explained as a statistical tendency of microscopic degrees of freedom that we do not see. We live, in this view, at the level of coarse-grained variables. Space-time and the gravitational field are like the smooth surface of a lake. The true dynamics are in the water molecules. Gravity is the way their unseen dance appears from far away. Several years later, Verlinde extended his ideas in a way that touched directly on the dark matter versus modified gravity debate. In work around the year 2016, he argued that when one includes the entropy associated not just with matter but with the dark energy that drives cosmic acceleration, an additional long-range effect emerges. This extra contribution to the entropic force could, in principle, mimic some of the phenomena usually attributed to dark matter in galaxies and clusters. In very broad strokes, the idea is this. The universe with a positive cosmological constant has a horizon, beyond which events can never influence us. That horizon carries entropy, associated with the dark energy-dominated vacuum. The presence of matter inside the horizon changes the entanglement structure and the distribution of entropy in subtle ways. As a result, at very low accelerations, there appears an additional elastic response in spacetime, producing an effective extra gravity that looks Mond-like, without explicitly altering Newton's law or adding particles. Some observational tests of these claims found encouraging agreement on galaxy scales. Others pointed to tensions, especially in the behavior of clusters. The community remains divided on how far these emergent gravity models can go. But again, the details of success or failure at this stage are not the main point. The main point is that gravity is being reimagined, not as a primitive field, but as a derived phenomenon from information theory and thermodynamics. There is a philosophical vertigo in this. The picture of gravity as geometry already asked us to let go of force in favor of curved spacetime. The picture of gravity as emergent asks us to let go, or at least to demote, spacetime itself. The smooth manifold of general relativity becomes a kind of bookkeeping device for entanglement. Distances and durations are not fundamental inputs. They are outputs of a deeper combinatorial structure. You can feel this most clearly in the slogans used by some researchers: space-time from entanglement, gravity from quantum information. These are not yet complete theories. They are directions of thought. They suggest that the basic building blocks of the universe might be bits, qubits, or something similar, whose patterns of correlation define what we experience as here and there, now and later, heavy and light. If this is true, the question of whether gravitons exist becomes more subtle. Just as phonons are quanta of sound waves in a medium, gravitons in an emergent gravity context would be quanta of collective excitations in the entanglement fabric. They would be no less real for that, but their fundamentality would be limited. Searching for them directly might be like trying to understand water by catching a single ripple on the surface, while the real story is in the molecules below. The thermodynamic hints go beyond Jacobson and Verlinde. In various derivations, one finds Einstein's equations appearing as statements about entropy bounds, as conditions for the monotonic flow of information, as consistency requirements in holographic dualities. There is a persistent sense that gravity and the second law of thermodynamics are more deeply linked than we yet understand. From an existential angle, this recasts gravity's intimacy. Earlier, we spoke of gravity as the universe touching you, keeping you on the ground, binding you to the planet, to the star, to the galaxy. In an emergent picture, that touch is mediated by the statistics of unseen microstates. The pull you feel standing on Earth is, perhaps, the way an unimaginably large information system relaxes toward equilibrium when a small piece of matter is misplaced. There is also a certain humility in this perspective. It suggests that what feels most basic in our experience, the solidity of the floor, the weight of our body, the curve of a falling path, is already a level of abstraction. We are, metaphorically speaking, like creatures who understand weather but not molecules, who have names for winds and storms but not for air. Gravity, in our language, is a name for a pattern in a deeper game we do not yet see. Critics of emergent gravity are quick to point out its current limitations. Many models work best in highly symmetric situations or in approximations that do not yet capture the full complexity of the real universe. Some of the claimed matches to galaxy data are sensitive to assumptions and data choices. The step from toy models in anti-de Sitter space to our expanding, approximately de Sitter universe is non-trivial. It is entirely possible that some of these ideas will fade, corrected, or replaced by more accurate frameworks. But even if specific proposals fall out of favor, the questions they raise remain. Why do black holes have entropy proportional to area, not volume? Why can Einstein's equations be derived from thermodynamic assumptions? Why does holography work so well in the cases where it does? Why does the structure of quantum entanglement seem to encode geometry so naturally? These are not accidents. They are structural puzzles. From the vantage point of this book, emergent gravity is another facet of the same deep unease. If gravity is fundamental, we want to quantize it and find gravitons. If gravity hides its quanta, we wonder about the limits of experiment. If gravity needs modification at low accelerations, we question our trust in its current laws. And if gravity emerges from entropy and information, we are forced to rethink what we even mean by a force or a field. Perhaps the most striking thing is how all these lines of thought, different as they are, converge on one intuition: that the geometry we move through is not primary. The stage on which we live, with its distances, durations, and curvatures, feels absolute because our senses are tuned to it. But the theoretical story keeps whispering that the stage might be built, step by invisible step, from combinatorial rules that have more to do with counting and correlation than with stretching rubber sheets. On a quiet night, when you feel the weight of your body against the bed and the pull of the planet holding you in place, it is tempting to think of gravity as the most straightforward fact in the world. Things fall, mass attracts mass, the Earth curves space-time, and you follow the curve. The emergent gravity perspective does not deny any of that. It only suggests that underneath the curve there might be a tapestry of information, that underneath the pull there might be entropy, and that what we call gravity is the way the universe, at its deepest, keeps track of everything it contains. If gravity can emerge from information, then there is another, almost opposite intuition tugging at it from the side. What if, instead of being woven from something deeper, it is simply not as long-ranged as we thought, because its carrier has a tiny, but finite, mass? In the standard picture, the graviton, if it exists, is massless. That is why gravity reaches across cosmic distances. A massless field has no natural range limit. Its influence fades with distance, but it never quite stops. The same is true of electromagnetism. Photons have no rest mass. And so, light and electromagnetic forces reach, in principle, arbitrarily far, only weakened by spreading out. Giving a particle a mass changes that. A massive force carrier mediates an interaction with a finite range. The classic example is the weak nuclear force. The W and Z bosons that carry it are heavy. That heaviness makes the weak interaction short-ranged. It becomes powerful only at tiny distances, inside nuclei, or in high-energy collisions. The question, then, is disarmingly simple to ask and alarmingly hard to answer. What happens if we give the graviton a mass? Would gravity become a force with a finite range, weakening more rapidly at large distances, perhaps explaining why the expansion of the universe speeds up without invoking dark energy? Could a tiny graviton mass be the key to cosmic acceleration? Physicists did not wait for quantum gravity to be fully developed to play with this idea. In the late 1930s, Marcus Fiers and Wolfgang Pauli wrote down a linear theory of a massive spin-2 field on a flat spacetime background. At the level of small perturbations, it made sense. The mathematics was well behaved. The field had the right number of degrees of freedom. It propagated with a mass term, giving it a finite Compton wavelength, a natural range. But when people tried to connect this linear massive theory to the nonlinear world of full gravity, problems emerged. In the 1970s, Van Dam, Veltman, and Zakharov argued that even in the limit where the graviton mass tends to zero, the predictions of massive gravity do not smoothly approach those of general relativity. Light bending by the sun, for example, would differ by a fixed fraction from Einstein's value, no matter how small the mass. Solar system tests seem to rule out such a theory. Shortly afterward, Arkady Weinstein pointed out that this conclusion might be too quick. He suggested that nonlinear effects, ignored in the simple analysis, could become important near massive bodies and restore agreement with Einstein at short distances. In regions of strong gravitational fields, the extra degrees of freedom associated with the graviton mass might hide themselves, leaving only tiny deviations at large scales where the field is weak. This became known as the Weinstein mechanism. As theorists tried to build fully nonlinear versions of massive gravity, they ran into another, more serious issue. Many constructions that looked acceptable at a glance turned out to contain ghost degrees of freedom. A ghost, in this context, is not a poetic word, but a technical one. It refers to a mode in the theory with the wrong sign of kinetic energy, leading to instabilities. Such a mode lets you create excitations with negative energy. And in quantum theory, that means catastrophic runaway processes. For a long time, the pattern repeated. You could either have a theory of massive gravity that was mathematically consistent but disagreed with observations, or one that fit known data but harbored pathological ghosts. Gravity seemed to resist having a mass in a healthy way. The mass term kept infecting the deep structure of the equations with problems. Around the year 2010, a breakthrough appeared. Claudia de Rham, Gregory Gabadadze, and Andrew Tolley constructed a particular class of massive gravity models, now often called DRGT theories, that seem to evade the Boulware-Deser ghost problem. By carefully choosing the form of the potential terms that give the graviton its mass, they showed that the dangerous extra mode could be eliminated, at least in certain regimes. The theory remains nonlinear, incorporates the Weinstein mechanism, and allows for a tiny graviton mass. Conceptually, giving gravity a mass in this way is like shrouding space-time in a thin fog. At short distances, near planets, stars, and in the solar system, the fog is so thin that you barely notice it. Gravity looks exactly like general relativity. At large scales, across galaxies and cosmological distances, the fog becomes thick enough that the force does not propagate unchanged. It weakens or shifts character, potentially altering cosmic expansion and structure formation. Observations quickly joined the conversation. Gravitational waves, detected from merging black holes and neutron stars, offer a clean way to test how gravity propagates over long distances. If the graviton had a non-zero mass, gravitational waves would not travel exactly at the speed of light for all frequencies. They would disperse, with lower frequency waves moving slightly slower. By comparing the arrival times and shapes of gravitational waves from distant events, and in some cases comparing them with electromagnetic signals from the same source, astrophysicists have placed strong upper limits on any graviton mass. Those limits, translated into the language of Compton wavelengths, tell us that if the graviton has a mass at all, its associated wavelength must be at least comparable to, or larger than, the scale of galaxy clusters, or even the universe itself. That is another way of saying that any finite range of gravity must be enormous. Over the distances of the solar system, and even across many galaxies, gravity behaves as if its carrier is effectively massless. Cosmology imposes additional constraints. The growth of large-scale structure, the pattern of galaxies and clusters traced in enormous surveys, depends sensitively on how gravity pulls on matter over cosmic time. Massive gravity models must be designed so that they reproduce the observed distribution of structures, the anisotropies of the cosmic microwave background, and the detailed expansion history inferred from supernovae and baryon acoustic oscillations. In many constructions, this requires careful tuning of parameters and sometimes strange behavior in the early universe. On the other hand, the very fact that such models can be made to fit at all is remarkable. It means that there are self-consistent worlds, close to our own in many ways, in which gravity fades differently at colossal distances because its messenger is endowed with an almost unimaginably small mass. In those worlds, the late-time acceleration of the universe might be a consequence of gravity's modified behavior, not a separate dark energy component. From an existential perspective, massive gravity plays with a quiet intuition. We are used to thinking of gravity as the most stubborn, universal connection. It keeps acting, gently but persistently, across every distance. To imagine it as having a finite reach, even one so vast that no single human mind can really picture it, is to entertain the idea that there are scales at which the familiar pull simply stops or transmutes into something else. There is also a more intimate layer to this. The weakness of gravity compared to other forces has always been a puzzle. The electric repulsion between two electrons is enormously stronger than their gravitational attraction. One way of framing this is to say that the fundamental gravitational coupling is tiny. Another, in the spirit of massive gravity and related ideas, is to say that what we perceive as weakness might be a side effect of the force being mediated by a massive, long-ranged field whose influence is diluted in subtle ways. Not everyone is convinced that massive gravity is the right road. The mathematical structure of these theories is intricate. They often require introducing not just a mass term, but an extra reference metric, or fields, that play the role of embedding spacetime into a larger structure. Some versions struggle with instabilities in cosmological solutions, or with superluminal propagation in certain backgrounds. The line between a clever modification and an over-engineered model is thin. Still, the effort is telling. It shows that even a century after Einstein, physicists are willing to take the core structure of general relativity and ask what happens if you tilt it, add a term, bend its symmetries. Massive gravity is, in a sense, a controlled act of heresy. It keeps the idea that gravity is geometry, but quietly adds a new ingredient to the geometrical field, turning the pure massless spin 2 graviton into a slightly heavier, more complicated entity. From the vantage point of this journey, massive gravity sits alongside MOND, dark matter, emergent gravity, and quantum gravity, not as a rival claiming the whole truth, but as another way of probing the same mystery. Each approach tweaks a different assumption. MOND alters the law in the weak field regime. Dark matter adds new content to the universe. Emergent gravity demotes spacetime to a derived concept. Massive gravity leaves the stage in place, but changes the properties of the actor who walks upon it. When you stand on Earth and feel your weight, none of this is apparent. The pull feels smooth, universal, unqualified. You cannot tell whether the thing holding you is mediated by massless quanta, by massive ones, by emergent information, or by a law that bends at low accelerations. The everyday experience is the same. The differences reveal themselves only when you stretch your imagination across billions of light years, or when you listen to the faint sigh of colliding black holes. In that contrast lies perhaps the most quietly unsettling aspect of gravity. It is familiar enough to be taken for granted, yet the space of possible explanations for it remains wide. We can imagine universes where gravity is a perfect, massless geometry, others where it emerges from entanglement, others where it carries a hidden mass that reshapes the fate of cosmic expansion. Our own universe might pick one of these stories or some mixture we have not yet written. To give gravity a mass is, in the end, to admit that even the range of the most universal of forces might be negotiable. That the bond between things could, at some scale, thin and fade. That the architecture of space-time, which we have learned to think of as fixed in its deep rules, might itself admit small, almost imperceptible flexes. And that, in those tiny flexes, written in terms too small for lived experience and too large for direct experiment, the universe might be hinting that even the basic categories with which we began this journey are provisional. If gravity might thin out across enormous distances, there is a still stranger suspicion behind it. Perhaps the distance we think we know is only part of a larger scaffolding, and gravity is fading not into nothing, but into directions we do not see. Picture a sheet of paper lying on a table. 2 ants live on that sheet. Their whole world, as far as they can tell, has only length and width. They can walk forward and sideways. They can draw maps, build houses, wage tiny wars, make tiny peace. If you lift the paper and fold it, their world warps. 2 regions that were far apart become close. 2 paths that looked straight now bend. To you, watching from above, this is simple. You have an extra direction in which to move the sheet. To the ants, who cannot step off the paper, the change is mysterious. Forces and motions seem to violate their simple geometry because they are leaks from a higher space. For much of the history of physics, extra dimensions belong to this kind of parable. In the early 20th century, some tried to unify electromagnetism and gravity by adding a small, curled-up dimension to space-time, so tiny that no particle could wander far along it. Later, in string theory, whole landscapes of extra dimensions appeared, compactified into shapes whose details controlled the kinds of particles and forces present in the lower dimensional world. These ideas were mathematically rich, but for the most part stayed far from experiment. At the end of the 20th century, a different kind of extra dimension proposal arrived. One that treated gravity in a new way. In some of these brain world scenarios, our familiar universe is a kind of 3-dimensional surface. A brain, embedded in a higher dimensional bulk. The particles and fields of the standard model are bound to the brain. They cannot leave. Gravity, however, can wander into the bulk. Its field lines are not confined to the sheet. In the late 1990s, Lisa Randall and Raman Sundram wrote down concrete models along these lines. In one version, our universe sits in a 5-dimensional space-time where the extra dimension is not simply large or small, but warped. The warp factor changes how distances and energies relate as you move along the extra direction. In another version, there is a single brain in such a warped space, and gravity, though allowed to explore the bulk, is still effectively localized near the brain at short distances, while changing character at larger scales. The intuitive picture is easier than the equations. Imagine that each point of our familiar space is really a cross-section of a higher dimensional structure. Most fields are tied tightly to that cross-section, like paint glued to the surface. The gravitational field, by contrast, is like a very fine mist. Most of it clings near the brain, but some of it can drift into the surrounding volume. Close up, the difference is negligible. Far away, the mist has spread, and the pull it exerts on the brain is weaker than it would be if it were confined. This leaking of gravity into extra dimensions offers a new way to explain its weakness. We feel only the fraction of the field that remains on our brain. The rest is diluted in directions we cannot access. In some constructions, the true fundamental strength of gravity in the bulk is much larger, comparable to other forces, but by the time it is projected down onto our 3-dimensional world, it appears feeble. These ideas are not just metaphors. They make predictions. Gravity, in ordinary 3-dimensional space, follows an inverse square law at distances above the size of the source. Double the distance, and the strength falls by a factor of 4. In higher dimensions, the same geometric reasoning applies, but the power changes. Field lines spread out into more directions. If gravity leaks into extra dimensions beyond a certain scale, the effective law on the brain should begin to deviate from the pure inverse square form at very small or very large distances, depending on the model. Experimentalists saw an opening. If there are additional spatial directions of millimeter size or smaller, the force between two masses separated by sub-millimeter gaps could betray their presence. Precision experiments were designed in which tiny test masses were brought close together and their mutual pull measured with exquisite care, compensating for electromagnetic and thermal noise. The results, so far, have found no deviations from the inverse square law down to fractions of a millimeter. Each null result translates into a limit. If extra dimensions exist of the simple types considered, they must be smaller or more strongly warped than those scales. Colliders offered another testing ground. In scenarios where the true quantum gravity scale in the bulk is lower than in four-dimensional thinking, high-energy collisions could produce miniature black holes or Kaluza-Klein gravitons, modes of the gravitational field that carry momentum into the extra dimension. Such events would show up as bursts of particles with specific signatures, or as missing energy events where momentum seems to vanish from our brain's accounting. The Large Hadron Collider has searched for such patterns. It has not found conclusive evidence for extra dimensions. Instead, it has set constraints on the parameters of brain-world models, pushing the scale at which gravity could become strong in the bulk to higher energies. Beyond the collider's reach, as with dark matter searches and graviton hunts, the absence of discovery so far does not kill the idea, but it tightens the space in which it can live. Gravitational waves offer a further window. In a universe with extra dimensions, ripples of spacetime might excite Kaluza-Klein modes, leading to additional polarizations or modified propagation at certain frequencies. The waves could bleed energy into the bulk, arriving weaker or distorted compared to predictions from pure four-dimensional general relativity. So far, the catalogue of gravitational wave events observed since that first detection in September of the year 2015 looks consistent with Einstein's theory in four dimensions. But the precision is still improving. The possibility of subtle leaks remains under investigation. What makes these brain world and extra dimension ideas especially haunting in the context of gravity is not just their mathematical form, but their psychological charge. They take the most taken-for-granted feature of our experience, that space has three dimensions we can move in, and quietly ask whether that might be a local illusion. They suggest that the weakness of gravity, the cosmic acceleration, and perhaps some aspects of dark matter effects could all be shadows thrown by a higher dimensional stage. Return, for a moment, to the ants on the paper. If one ant drops a pebble, it rolls along the sheet in a way the ant can predict with its two-dimensional physics. The equations work. The pebble follows the paths allowed. But if a giant hand above the paper tilts the sheet slightly, the ant sees the pebble accelerate in a direction that does not fit its equations. To explain it, the ant can either modify its laws or imagine a new, unseen influence. Only by discovering the existence of the third dimension does the pattern become simple again. We are not ants, and the universe is not a literal sheet of paper, but the analogy carries a message. Our best gravity theory may be a projection, a lower dimensional view of a higher dimensional reality. The places where our equations struggle singularities, cosmic acceleration, galaxy rotation curves, might be the spots where higher dimensional dynamics poke through. There is, of course, a danger in such thinking. Extra dimensions can be added too easily as a cure for any mismatch. You can always say that something unobserved in a direction you cannot see is responsible. That is why serious models tie the extra dimensions tightly to specific, testable consequences. Warped geometries have particular signatures. Leaking gravity changes specific observables. Not every wild higher dimensional story earns the right to be called physics. Still, the fact that some carefully built extra-dimensional models remain consistent with known data, and sometimes even offer new ways to see old puzzles, keeps the idea alive. It is part of a wider pattern we have been tracing. When gravity misbehaves according to our expectations, One class of response is to change the content of the universe. Another is to change the law, and a third is to change the stage on which the law plays out. From an existential angle, hidden dimensions add a peculiar flavor to the human place in the cosmos. They suggest that what we call here and there might be slices through a richer elsewhere. That events we interpret as fundamental might be projections of a deeper choreography, that the bonds which hold galaxies together and shape the fate of the universe might be the side effects of geometry in directions we will never be able to point to on a star map. It is important to be honest about how speculative this is. No experiment has yet forced us to accept extra dimensions. General relativity in 4 dimensions, plus dark matter and dark energy, still describes observations extremely well. Many physicists treat brain-world scenarios and warped extra dimensions as useful theoretical laboratories, places to test ideas about gravity, rather than as literal blueprints of our world. And yet, even as laboratories, they leave a mark on our imagination. They make it easier to accept that our intuitive picture of space is not sacred. They show that the equations of gravity can be embedded in larger structures without losing their local successes. They remind us that the very notion of a fundamental number of dimensions is less settled than it appears when we stand in a room and stretch out our arms. On a quiet night, if you walk under an open sky and feel the familiar pull of Earth under your feet, it is almost impossible not to think of that pull as emanating from the planet in the 3 dimensions you know. The extra dimension, if it exists, does not add a new direction for your body to move in. It would be felt only through differences in how gravity behaves in extreme situations, through delicate shifts in the way galaxies cluster or waves ripple. Perhaps that is the most humbling part. If gravity leaks into hidden dimensions, it does so in a way that never disrupts your footing, never announces itself in daily life. It hides in the decimals of measurements, in the tails of distributions, in the slight bends of cosmic filaments. It lives where our direct intuition ends and our equations must take over. Like so many other possibilities in modern gravity, it asks us to accept that the universe may be quietly more spacious than we can ever fully picture, and that the familiar downward pull we feel is only one component of a field that extends into a larger, unseen architecture. If the space you move through might be only a slice of something larger, then the question waiting underneath all of this is quieter and more personal. How much of what you call reality depends on everything else that exists, and how much is simply written into you from the start? Ernst Mach, a 19th century physicist and philosopher, liked to begin with very simple experiences. Imagine, he said, that you are standing under a clear night sky and you begin to spin with your arms outstretched. You feel your arms pulled outward. Your body leans. There is a sense of a force, something trying to fling you away from the axis of your own rotation. We call it centrifugal. But relative to what are you rotating? If you stripped away the stars, the galaxies, all distant matter, leaving only you and empty space, would you still feel that outward pull when you spin? Is inertia, the resistance of your body to changes in motion, something that belongs to you alone? Or is it a kind of conversation with the entire universe? Mach's suggestion, phrased loosely, was that inertia here depends on matter everywhere. The distribution of mass in the cosmos might determine the inertial frames, the special states of motion in which Newton's laws take their simplest form. In that sense, there is no truly isolated object. The way you move when unforced, the meaning of straight line and constant speed, is entangled with the distant stars. This idea, often condensed under the label Mach's principle, fascinated Einstein. As he built general relativity, he hoped that the geometry of space-time and the inertial structure it carries would be fully determined by the matter within it. No absolute background, no fixed stage beneath the actors. Everything would be relational. Matter and geometry would define each other. General relativity partly fulfills this dream. The presence of mass and energy curves space-time. Free fall is not motion with respect to a rigid absolute grid, but motion along geodesics in a geometry that all the matter helps shape. Yet the theory also allows solutions in which space-time has structure, even when no matter is present, waves and curvature propagating in vacuum. The status of Mach's principle inside relativity remains ambiguous. Some aspects are realized, others are not. Why does this matter for our story about gravity's mystery? Because Mach was pointing to something that all the later developments only sharpened. The idea that the behavior of a small piece of the world may depend in subtle ways on the whole. Singularities tell us that the global structure of space-time can break our local predictions. Gravitons, if they exist, would knit together the quantum fluctuations of the field across vast distances. Dark matter, MOND, emergent gravity, massive gravity, extra dimensions, all tell different stories about how the local pull we feel might be anchored in a much larger pattern. When we looked at Dyson's impossibility arguments, we brushed against a boundary between what is real and what is, perhaps, forever unobservable. That boundary is not fixed by our preferences. It is written into the interplay between quantum mechanics and gravity, between measurement and collapse. The same tension appears when we ask whether black hole singularities are literal places or signals of theory failure, whether dark matter is a new substance or a sign that gravity's law is incomplete, whether spacetime is fundamental or emergent. At this point, it is natural to look for guidance in the philosophy of science. Karl Popper famously suggested that a theory should be considered scientific if it makes risky predictions that could, in principle, prove it wrong. Falsifiability, in that sense, is a virtue. General relativity passed such tests spectacularly, from light bending to gravitational waves. Some versions of MOND, massive gravity, and extra-dimensional models also make sharp predictions that can be checked and have been constrained. But Popper's criterion becomes harder to apply cleanly in the borderlands where gravity lives now. A quantum gravity theory that predicts gravitons we can never detect directly, or singularity resolutions that occur behind horizons we can never probe, may still yield indirect predictions. A dark matter model can be falsified for a given particle candidate, while the larger idea of dark matter as a class remains viable. An emergent gravity framework might reproduce Einstein's equations and their tested consequences, while differing only in regimes we cannot yet access. Thomas Kuhn, looking at the history of science, described a different pattern. Paradigms, he said, are overarching frameworks in which scientists work. Within a paradigm, puzzles are solved using shared assumptions. When anomalies accumulate and can no longer be brushed aside, a shift can occur, and a new paradigm reorganizes how data are seen. The same observations are reinterpreted through a different lens. Gravity, today, is a textbook case of this process in motion rather than in retrospect. For some researchers, the standard paradigm is Einstein's general relativity plus cold dark matter and dark energy. For others, the paradigm is that gravity must be modified in the low acceleration regime, and dark matter is a placeholder. For others still, the real paradigm shift is that gravity is emergent from quantum information and thermodynamics, and both dark matter and dark energy are effective phenomena in a deeper statistical picture. These communities often look at the same data sets: rotation curves, gravitational lensing maps, cosmic microwave background spectra, gravitational wave catalogs, Gaia star motions. They agree on the raw measurements, but they fit them into different stories. When a new result appears, it is filtered through these lenses. What looks like supporting evidence in one frame can look like a tension in another. Kuhn would say that we are living in a period of overlapping paradigms around gravity. There is no revolution in the dramatic historical sense yet. No sudden overthrow of Einstein. No single new framework that everyone accepts. Instead, there is a coexistence of narratives, each incomplete, each carrying part of the truth. That coexistence is not a failure of physics, it is a snapshot of physics as it works at the edges of understanding. What, then, is gravity really telling us through all of this? Perhaps the first message is that the world is more relational than we once thought. Your weight is not just about you and Earth, it is tied, through geometry and energy, to the structure of the universe at large. Inertial frames, free fall, horizons, even the direction of time's arrow in cosmology, all connect local experiences to global conditions. The second message is that explanation always has a horizon. Newton's law told us how masses attract. It did not say why. Einstein told us that masses curve space-time. The theory does not tell us why space-time exists or why it responds to energy in exactly that way. Quantum gravity approaches tell us there might be deeper microstructures or holographic dualities or entropic principles. They do not yet tell us why reality is built that way rather than another. The third message is more personal. The limits we encounter in trying to quantify gravity are also limits on ourselves. We cannot experimentally step inside a singularity. We cannot currently reach the Planck scale where space-time may become grainy. We cannot, most likely, hear a single graviton. Our instruments are made of atoms and fields that obey the same equations we are testing. Gravity drags on our mirrors and detectors even as we point them outward at the sky. Seen from that angle, gravity becomes a kind of mirror. On one side, it shows us galaxies, black holes, cosmic webs, the expansion of the universe. On the other, it shows us the contours of our own ways of knowing. Where the field becomes too strong, our classical maps tear. Where the field becomes too delicate, our quantum probes fail. In between, we build theories and ask which questions are meaningful and which are only reflections of our chosen language. None of this turns gravity into a metaphor only. It remains a real, physical interaction, the architecture of motion. But it does mean that living with gravity, intellectually, involves accepting that some questions may remain open for a long time, that different frameworks may coexist, and that what we call understanding is often a layered thing. We can navigate planetary orbits with near-perfect accuracy and still argue, in good faith, about whether the deeper story is geometric, emergent, massive, higher dimensional, or something else entirely. So perhaps what gravity is really telling us is not a single, hidden sentence about the universe, waiting to be decoded, but a set of constraints and invitations. It constrains what kinds of worlds are possible, which structures form, which stars live long enough, which planets hold onto air and oceans. It invites us to connect the intimate with the cosmic, the heaviness in our legs with the curvature of space-time, the drift of starlight with the shape of the whole. Somewhere, a person steps out into a city blackout and looks up. The sky is darker than usual. More stars than usual are visible. They feel the pavement under their feet, the pull in their spine, the weight of their own body. They know, vaguely, that this same gravity is shaping the orbits of those stars, the dance of galaxies, the slow evolution of the universe. Between those two sensations, personal weight and cosmic architecture, lies all of modern physics, and all of its unanswered questions. If you have stayed with this journey, you have not been given a final verdict on what gravity is. Instead, you have seen how each serious attempt to answer that question opens another door. If you want to keep walking through those doors, to sit with the uncertainty rather than rush past it, you are welcome to stay, to listen, and to let that quiet, familiar pull keep bothering you in new ways.